Uh, Welcome to the Transducers lecture 4. As usual, let us recollect what we have learned so far. We learned the characteristics of transducers, resolution, full scale, sensitivity, uh, uh, proof range or overload factor, accuracy of a transducer, precision, right, of a transducer. We have systematic accuracy as instrument errors and loading errors, right? uh, when we talked about these transducers, I did not specifically state uh, that any of the other adjectives when it comes to resolution or full scale or sensitivity or proof range. We call this as static characteristics. That is, input is constant and you define input output relationship in that sense. Uh, Before going to dynamic characteristics, there is one small thing I left over, and also there is an error when I was discussing the propagation of errors when random errors are present, right? Precision is random errors. So you have the average value is the best value plus deviation. So you have RMS or standard deviation. You have peak deviation, so can be unipolar or bipolar, right? And we also learned what happens if I start computing with measured values with errors. We derive two formulas. The second formula, the precision, uh, there is a small error in my derivation. I will go back to that in a little while. Let's continue with this. Now, if I look at a transducer, I can use this as a black box. I have my input, maybe this is temperature, and I have an output, maybe digital value, right, or a voltage value, whatever it is, right? And to get that, we need excitation, right? This is a general one. There are transducers that do not know that do not need external power, which means this is not required. I give the input, I get the output, right? A simple example is, all of you would have done machines laboratory, right? In the machines laboratory, we would have used what is known as a tachometer. What is a tachometer? It measures rotational speed of a shaft. Right? We say 1000 RPM, 1423 RPM, and so on. And I'm not sure what kind of tachometer you've used. The simple tachometer is called tacho generator. If you look at the DC generator with permanent magnet, the speed versus output voltage, right? This is speed versus output EMF. These are very proportional characteristics, and all I have to do is put a DC generator and drive it at the shaft speed and measure the output using a voltmeter. So I will get a very nice way of measuring the rotational speed of the shaft in terms of, I can calibrate in terms of rotations per minute or simply RPM, right? Output EMF, this is speed RPM. So this does not require any external power. It will generate an output on its own. So that kind of transducers where you do not need additional power, transducers without excitation power are called active transducers. Right? Active transducers are not the transducers that use active circuits. That's completely different. An active transducer is one which doesn't need external power supply. Of course, if you need an external power supply for the transducer to work, then you call this as passive transducer. Right? So that's one way of looking at the transducers and saying, oh, this transducer requires external power, so it is passive. This transducer doesn't require an external power, hence it is an active transducer. The second thing is, if I look at the characteristics here, the input is speed, output is EMF, I get nice characteristics. So this is called the input output characteristics of a transducer, right? So if I have my input here, my output here, whatever is the output, it could be variation in resistance, or it could be an output voltage, output current, an output charge, or simply a digital value, right? I will have a characteristics something like this. I may not have, I am assuming that I have a characteristic like this, where zero input gives me zero output, and if I have an input of 1, that gives me X. If I have an input of 2, it gives me 2X, and so on. Okay. So if I get a particular characteristics, then I call this characteristics a linear characteristics. Right? So What is a linear characteristics? We simply say the characteristics is linear if the input-output relationship obeys the laws associated with linearity. Now, what are the laws that you need to fulfill to get a linear characteristics? One is called cumulative law. I call this as input X and this is output Y, right? So cumulative law says if I am getting Y1 for an input of X1, or I will put the other way around, that's better, right? If I give an input of X1, I get Y1 as the output. If I give an input of X2, I get Y2 as the input. Now if I give X1 plus X2, if my output is Y1 plus Y2, then cumulative law is satisfied, right? So if I give 1 degree, I get 1 volt, I get 3 degrees, I get 3 volts. I give 1 plus 3, 4 degrees, I get 4 volts, right? Then it's a linear characteristic. Then it's not enough. This is only part of the necessity. It's not a sufficient condition. So the sufficient condition is called associative law. If I give x1, I get y1. If I give ax1, where a is a constant, I should get ay1, right? So this is known as the associative law. So both must be obeyed for a transducer to have a linear characteristic. So the only characteristics that would fit the linear is a straight line, right? That passes through origin. So I must have y equal to mx, right? But many times what we will get is y equal to mx plus c, right? This is a general straight line, so I can draw this. So this is y is equal to mx plus c. So when x is equal to 0, I get c. We call this as c as a y-intercept at x is equal to 0, or we can also say that it is an offset at 0. So even though strictly speaking y equal to mx plus c does not obey the cumulative and associative laws, but still it's a linear one. Only thing is it has an offset. If I remove c, it becomes a linear. So we simply say that this is a linear characteristics, but with an offset, right? So offset is another kind of error. Most manufacturers will give you offset, and many transducers not only have offset but offset drift, where the c is a function of time. So if I look at c, maybe now it is only 20 millivolts, and maybe after 1 hour of heating it becomes 27 millivolts, right? Something like that. So c can be an offset or offset drift. So I get, if c is constant, I get offset. If c is time varying, then I get offset drift. So we'll have to be very careful. But many times we may not get a linear characteristics. So it's possible that I have something like this. So this is output, this is input, and this is the characteristic I get from the transducer. I have no choice, right? So what we do is that we use linear regression and put a straight line curve fitting, right? This is y equal to mx plus c, right, where m is the slope. And we say that this transducer has a characteristics, linear characteristics, but it also possesses nonlinearity. What is nonlinearity? The actual value of the transducer from the expected linear value. Of course, this expected linear value is something that we arbitrarily put derived it from the nonlinear actual nonlinear characteristics of the transducer. Okay, so this is the nonlinearity error. So again, if I look at it, the nonlinearity error depends upon where I measure. If I measure here, I get some nonlinearity error. If I measure here, nonlinearity error equal to 0, right? And we can look at that. So sometimes manufacturers give you this curve and also give you the linear fit, right? And specify what is the offset and what is the slope. The slope is also known as the sensitivity because it's delta V naught by delta V in, right? The slope of a straight line is delta x by delta y by delta x, and hence the slope is the sensitivity of the transducer. So, but in many cases it may not be possible for the transducer to give you the curve that is given in the violet color, right? So what is looks at is, again, he looks at the error at different points, and he takes the maximum of that error, maximum nonlinearity error. He divides it by the full scale into 100, then it is called full scale nonlinearity error, right? So once again, you will have to be very, very careful. If a transducer manufacturer tells you my transducer has a nonlinearity of 1%, it need not be 1% at all points. What he's really trying to say is that the maximum nonlinearity divided by full scale into 100 is 1%. So you will have to be very careful when you use such transducers. Identify where the maximum nonlinearity occurs and try to avoid having your input at that point, or at least you know that nonlinearity exists, right? And we we will, as we start learning transducers, we will learn about come across all this, right? And so the in most cases we would like to get a nice characteristics like this. We do not want an offset, we do not want, right? So 0 for 0 and full scale for full scale. So manufacturer transducer, if I look at it, I may not get this. I may get a characteristic like, oh, okay, I'll just erase this. So let me put this. I want this characteristic from a transducer, but I may get something like this, right? So we see that not only at 0 there is an offset, so this we call it as offset, but even the sensitivity of the transducer, this is m expected, and this slope is m actual, right? If I write the straight line as y equal to mx plus c, here I am going to get me, and this is going to be ma. So apart from the nonlinearity error, even if the transducer is linear, we may have an error in the sensitivity, right? The transducer manufacturer would say that my transducer will give you an output sensitivity of 100 millivolt, 1 millivolt per kilopascal, right? Uh, with a gain error of 1%. What that gain error means? The gain, as I said, is output by input, right? And delta output by delta input, if I get a linear characteristics, the slope of the characteristics linear line that I get uh, can be thought of as gain, right? I'm getting giving an input, I'm getting an output, right? So the gain error is m actual minus m expected by m expected into 100%. Again, this is uh, most transducer manufacturers will provide you this data saying that my transducer has a gain error, in the worst case gain error of 1%. So it's not a big problem. Every transducer you take, you uh, get the input output characteristics, and then you can find out what is the offset and what is the gain, and use it for actual measurements. So that would be really troublesome if you have such characteristics, but you have no other go but to calibrate each and every transducer that you make, right? Again, many uh, transducer manufacturers do this. They give you, when they give you a transducer, they get the input output characteristics and give you a graph on the input output characteristics. Um, the nonlinearity again is with respect to an assumed linear input output characteristics. Please remember that if your transducer possesses a nonlinearity, it's not the actual nonlinearity that um, is represented. You assume that the output is linear and give a linear characteristics as y equal to mx plus c, and then whatever error that the actual characteristics has with respect to this assumed linear characteristics is called the nonlinear error, right? Okay. What is this coming here? Okay, not a big problem. Okay. Uh, Now uh, the one error that I made is variance sigma y square equal to dou f by dou x1 into sigma x1 square plus dou f by dou x2 into sigma x2 square, and so on. Please correct this if you are taking earlier notes, or if you are using my earlier video. This is the correct one. You can actually derive this. That's not a big problem. So all these characteristics come under static characteristics, where my input is not changing and the output has attained steady state. Now, what do we mean by output as attained a steady state? Last class, at the end of the class, we did understand or learned what is, right? So, if my input is suddenly given, let's say this is my body temperature 37.4 degrees centigrade, I give to a thermometer, right? And if I look at the output of the thermometer, it goes like this. It depends upon what kind of thermometer used. Some have take a long time, some give readings within, right, this. So this period where the output is not reflecting. So here I get 37.4 degrees centigrade attained, right? And in terms of mathematics, we'll see that it's not really that easy to get a steady state. But in a practical, we say this is transient. Oh my God. Okay, so this period is transient, and this is steady state. Right? So we call this as the settling time of transducer, right? The settling time of the transducer is simply called the time required for the transducer output to attain the final value. What is the final value? We will see that if I really start uh, using mathematics, it may not be possible to get the final value for a very, very long time, right? So we define settling time uh, it is also called the response time. Sometimes we call this as latency, delay, all means the same thing, okay? Is the time taken for the output of the transducer output of a transducer to attain within plus or minus x% of the steady state or expected output, right? Okay, so if nothing is specified, x is assumed to be 1%. That is, if you reach within 1% of the final output after some time, that time is taken as response time or settling time, right? The there is also another characteristic of the transducer. Again, uh, these all come under dynamic characteristics. Once again, I tell you, this is input is not changing, right? So we will also have another dynamic characteristics where my input itself is dynamic, right? My input is also changing with respect to time, and the output also has to change with respect to time, and there will be a relationship between the input output. So this is for input is static. Input doesn't change with respect to time. Now the other characteristics is called the slew rate of the transducer. The slew rate is the change in the output delta out by delta in during transient, right? So it's slope of the way the output is uh, changing, right? Slew rate is very important. We will find out when we do assignments that it's not enough that we have other characteristics satisfied. Slew rate also has a very important role to play in getting a proper output from a transducer, right? Uh, Now, so far we looked at uh, the input being static or input being constant. It's not time changing. When my input is a function of time, right? Then there are two possible characteristics, right? When my input is a function of time, we call this as dynamic input, right? So when I have dynamic input, I get dynamic input output characteristics. Dynamic input, dynamic output characteristics. Okay. So what do I mean by my input changing with respect to time? So this could be my input. This is time. This is my input. It keeps changing with respect to time. It's also possible that I have a, this is with respect to time, this is x, right, or input. So this is aperiodic. We call this as aperiodic signal, and this is periodic signal. Again, periodic signal can be of different types. I can have a transducer input like this, or I can also have something like this, right? All are repetitive function, so they have a periodic signal. Now, the moment I have dynamic input, it doesn't matter whether I have a periodic signal or an aperiodic signal. I need to define the input output characteristics for such signals in my transducer, right? So what do we do? Because I don't know what kind of input that I am going to get, all I know is that it is going to change with respect to time. Okay. So what do we do? Then we say, okay, I cannot define an input output characteristics unless otherwise I know what type of dynamic input I am going to give, right? And from that characteristics, it should be possible for me to obtain a dynamic input output characteristics for any kind of time varying signals, right? So what we have actually expressed in so many words right now is that I have a dynamic input, right, which I can find the characteristics of the transducer for any other dynamic input. Such a dynamic input I call a standard dynamic input. This is not particular to transducers. Whenever we talk about time varying quantities, we do come across this problem, right? For example, even building an amplifier, right? When I give a time varying input to my amplifier, I will have to define the amplifier characteristics for such time varying input. So what do we do in terms of circuit analysis? We put the dynamic input as sine or cosine signals, right? So I simply assume my input is root 2 x root 2x cos omega t, right? That is my input. It could be temperature, it could be pressure, it doesn't matter, it's a time varying input. Now if I give my input like this. I give this to my transducer. I should get an output. Of course, I should get Y the same, right? I can get some K times root 2 X. I put Xn so that we continue cos omega t, but in general I can also have a, let me write this y equal to k times root 2 x cos omega t plus y. So if I don't get the same frequency, the transducer is not linear. If the transducer is linear, if I am given sin omega t, I should get sin omega t. But in a practical situation, I may have a phase shift. Having a phase shift is not a big problem. We can handle phase shifts, right? So what I do is now I change omega, right? I change omega, my input frequency, and I find out what is the transducer characteristics y. The best is, of course, y as a function of input itself, right? So I will keep root 2 xn constant, vary only frequency, and I will get a characteristics. So I may get a characteristic something like this, right? Very possible. Okay. So if I look at this signal, the root 2, right? We call this, let me write it here once again, root 2 x cos omega t. We call this as the amplitude of the signal. This is the angular frequency given in radians per second. Radians per second. And from our circuit theory, we also know omega equal to 2 pi f, where f is the frequency given in hertz or cycles per second, and time t equal to 1 by f, right, is known as the period of the signal, right? So sin omega t or cos omega t are repetitive signals. They are also known as power signals, because you can calculate what is the power in a sin omega t or cos omega t signal, but you cannot calculate what is energy. Energy can be calculated only if I know how long the signal has been applied. Okay, so t period is given in seconds, right? That is 1 by f. So for example, if my input changes every 1 second, then my period is 1 second and the frequency is 1 by 1, which is 1 hertz or 1 cycles per second. The characteristics that I get as I vary my input is known as the frequency response characteristics of right? We obtain a frequency response characteristics by choosing the input to be either sin omega t or cos omega t. It doesn't matter, you can use anyone, with amplitude constant and frequency changing, right? So in general, a frequency response characteristics with respect to omega, you will have amplitude response. with respect to omega, you also have phase response, right? In general, output can have a phase shift, even with linear transducers. So we get the frequency and amplitude and phase response known as the frequency response of the transducer, right? uh, Now if I look at the frequency amplitude response of the transducer, right, uh, it's possible that I have my transducer, this is omega, this is amplitude, I get something like this, and then after a particular frequency I don't get the output, right? We call this as low pass characteristics. Normally the terminology came from the filter circuits, so we don't say LPC, we say LPF, low pass filter characteristics. It has a characteristic something similar to the low pass. So uh, frequencies less than FC are passed. So 0 to FC we call it as pass band, and this we call it as stop band, right? So I can also get a characteristics something like this. We call this as FCL, low pass filter cutoff frequency, FCH. My transducer doesn't respond from 0 to FCH, and it responds only, again, this is omega and this is omega CH, okay, and I can also use F. Let me use F so that you don't get confused. So this is FCL, this is frequency F, again this is frequency, this is amplitude, and this is FCH, high. So this is pass band, this is stop band. So we call this as, of course all of you know, high pass filter characteristics. There are two other characteristics that are possible. One is something like this. So I have F1, F2, and this is called band pass filter or band pass characteristics. The output is available only between a band of frequencies. So this is pass band. It's also possible that I get a characteristics like this. Between F1 and F2, this is again F, this is amplitude, this is F, this is amplitude, right? I can, my transducer does not work or gives me zero output between two frequencies F1 and F2. We call this as band reject. This is band pass filter, this is band reject filter, which is also called notch filter, right? So this is pass, this is also pass band, this is stop band, right? So when I talk about the dynamic characteristics of a transducer, the dynamic characteristics of a transducer simply means that my input is a dynamic input. When do I say my input is a dynamic input? When the input changes with respect to time. And when the input changes with respect to time, there are two possible scenarios. One is that I have an aperiodic signal, it simply changes with respect to time, no characteristics, or the input changes periodically with respect to time. One simple such input is, as we have already seen, sine theta, sine omega t, and cos omega t signals, which are repetitive with a period t, where t equal to 1 by f and 2 pi f is equal to omega, right? All those things we know from our UG itself. Okay, so the frequency response characteristics of a transducer can be four types. One is called the band pass filter, low pass filter characteristics, high pass filter characteristics, band pass filter characteristics, and notch filter uh, characteristics. Okay. Now, this is very easy to understand if you put that. But if I take an actual transducer and get the frequency response, F versus amplitude, I am not going to get something like this, right? It would be some value, almost remains constant and start reducing and moves to 0 at some time. Okay. So here also, if I see, I have a set of frequencies which are low enough that can pass, and a set of frequency that are high enough that is stopped. Okay, but I don't know where to put a pointer and say below this pointer this is pass, above this pointer it is stop, because it's continuously changing, not like the brick wall, right, where it suddenly drops after F1. So I will have to put an FC, right, such that I say that below FC all my frequencies are passed, but still it's not really correct, right? I should have got like this, but it's already changing, and above FC that it is stop, right? It's a kind of via media or compromise, I would say. Now, how do I choose the FC? At what kind of condition I put so that I can define my cutoff frequency below which it is a pass band, above which is a stop band for a low pass filter, right? This is LPF. Now, people came across this 120 years ago, and they said, okay, what is more important? Power, right? If the power in the output of a transducer is half the expected power, then that is the cutoff point. So the FC is chosen where my power, let's say I am going to get a power here, right, and at this point this is P by 2, where my power is half the expected power, right, and the band of frequencies which are passed, that is 0 to FC, so we call this as pass band, right. The pass band itself is known as bandwidth, right, and because we chose the cutoff frequency as the point at which the power becomes off, we call this as off power bandwidth, right. We simply say that the band of frequencies that are less than half the expected power is called pass band. Band of frequencies that are above where the power is less than half the expected one is a stop band, so which is called half power uh, bandwidth. So I will stop here. We will continue in tomorrow's class. Okay, I'll see you tomorrow.